In the last video, we simulated a story about a person flipping a coin. We did this to get the probability of each possible outcome of the story. That set of probabilities is called a probability mass function, or PMF. A PMF is defined as the set of probabilities of discrete outcomes. To understand how this works, consider a simpler story, a person rolling a die once. The outcomes are discrete because only certain values can be attained. You cannot roll a 3.7 with a die. Each result has the same or uniform probability, 1/6. For this reason, the PMF associated with this story is called the discrete uniform PMF. Now, the PMF is a property of a discrete probability distribution. A distribution is just a mathematical description of outcomes. We can match a story to a mathematical description of probabilities, as we have just seen with the discrete uniform distribution. Now, the story we simulated in the last video corresponds to the binomial distribution. Its story is as follows. The number R of successes in n Bernoulli trials with probability P of success is binomially distributed. The number of heads in 4 coin flips matches this story, since a coin flip is a Bernoulli trial with P equals 0.5. We call the function np.random.binomial with 2 arguments: the number of Bernoulli trials, coin flips, and the probability of success, 0.5. We get 2 heads out of 4. We want to repeat the 4-flip experiment over and over again. So again, we can specify the size keyword argument, which tells the function how many random numbers to sample out of the binomial distribution. To be able to plot the binomial PMF, we'll draw 10,000 samples from a binomial distribution where we do 60 Bernoulli trials with a probability of success of 0.1. If we do this over and over and tally the results, we can plot the PMF. As expected, the most likely number of successes is 6 out of 60, but we may expect to get as many as 11 or as few as 1. Unfortunately, while this is a proper way to display a PMF, it is not the easiest to implement with Matplotlib. You'll plot a PMF as a histogram in the exercises. Now, the CDF is just as informative as the PMF and easier to plot, just as we have done before. And here it is. Now that you know the story of the binomial distribution, have a feel for how it looks, and know how to sample out of it, let's do some hacker statistics with it. In his great book on information theory, statistical inference, and machine learning, David MacKay described a town called Poissonville, where the buses have a very erratic schedule. If you stand at a bus stop in Poissonville, the amount of time you have to wait for a bus is completely independent of when the previous bus arrived. In other words, you could watch a bus drive off, and another one will arrive almost instantly, or you could be waiting for hours. Arrival of buses in Poissonville is what we call a Poisson process. The timing of the next event is completely independent of when the previous event happened. Many real-life processes behave in this way. For example, natural births in a given hospital are a Poisson process. There is a well-defined average number of natural births per year, and the timing of one birth is completely independent of the timing of the previous one. Another example is hits on a website. The timing of the next hit is independent of the timing of the last. There are countless other examples. Any process that matches the buses in Poissonville story is a Poisson process. Now, the number of arrivals of a Poisson process in a given amount of time is Poisson distributed. The Poisson distribution has one parameter, the average number of arrivals in a given length of time. So, to match the story, we could consider the number of hits on a website in an hour with an average of 6 hits per hour. This is Poisson distributed. Let's take a look at the PMF for this example. For a given hour, we are most likely to get 6 hits, which is the average, but we may get more than 10 or possibly none. You might notice that this looks an awful lot like the binomial PMF we looked at in the last video. This is because the Poisson distribution is a limit of the binomial distribution for low probability of success and a large number of Bernoulli trials, i.e., for rare events. You'll explore this relationship further in the following interactive exercises. Now, to sample from the Poisson distribution, we use np.random.poisson. It also has a size keyword argument to allow for multiple samples. Let's use this function to generate the Poisson CDF. After that, it is the usual procedure of computing the eCDF, plotting it, and of course labeling the axes. The result, predictably, looks like the binomial CDF we saw in the last video. Now let's get some experience with the Poisson distribution in the exercises. So far, we have talked about probabilities of discrete quantities, such as die rolls and number of bus arrivals. But what about continuous quantities? A continuous quantity can take on any value, not just discrete ones. For example, the speed of a train can be 45.76 kilometers per hour. Continuous variables also have probability distributions. Let's consider an example. In 1879, Albert Michelson performed 100 measurements of the speed of light in air. Each measurement had associated some error with it. Conditions such as temperature, humidity, alignment of his optics, etc., change from experiment to experiment. As a result, any fractional value of the measured speed of light is possible, so it is apt to describe the results with a continuous probability distribution. In looking at Michelson's numbers, shown here in units of megameters per second, or thousands of kilometers per second, we see that this is indeed the case. What probability distribution describes these data? I posit that these data follow the famous normal distribution. To understand what the normal distribution is, let's consider its probability density function, or PDF. This is the continuous analog to the probability mass function, the PMF. It describes the chances of observing a value of a continuous variable. The probability of observing a single value of the speed of light does not make sense because there is an infinity of numbers, say between 299.6 and 300.0 megameters per second. Instead, areas under the PDF give probabilities. So the probability of measuring that the speed of light is greater than 300,000 kilometers per second is an area under the normal curve. Parametrizing the PDF based on Michelson's experiments, this is about a 3% chance, since the pink region is about 3% of the total area under the PDF. To do this calculation, we were really just looking at the cumulative distribution function, or CDF, of the normal distribution. Here is the CDF of the normal distribution. Remember that the CDF gives the probability the measured speed of light will be less than the value on the x-axis. So reading off the value at 300,000 kilometers per second, we see that there is a 97% chance that a speed of light measurement is less than that. So there is about a 3% chance that it is greater. We will study the normal distribution in more depth in coming exercises. But for now, let's review some of the concepts we've learned about continuous distribution functions.